Bismillahirrahmanirrahim. Hello ladies and gentlemen, I would like to try to continue chapter 1.8. It's depends to the Green's function, Green's theorem in mathematics, and I usually this theorem we use usually this theorem in physics in different kind of different branch of physics like thermodynamics or electromagnetism and so on. What is the Green's theorem? This theorem is a powerful tool for treating electrostatic boundary value problems, and is a simple application of the divergence theorem. It means if you use this equation or this relation for the divergence theorem, as you know, integral of diverge A on volume is equal to A dot n dA. dA is a area element of the surface that the volume V surrounded by the surface, and theta is the angle between A and n. N is a normal vector, normal unit vector, in fact. So let's we change A with a vector. This vector is an arbitrary vector, phi gradient of psi. So phi and psi are arbitrary functions, scalar functions of position. The phi and psi just varies with the position or with the distance. So diverge A is equal diverge phi gradient psi, and you can use an equation with this. In fact, you take phi first. Phi diverge gradient psi is equal Laplacian psi times phi plus gradient psi dot gradient phi. So you can write this equation. A dot n is equal phi gradient psi dot n. So you can just use dot. You can use let me tell you what gradient psi dot n. You can use this equation and use these relations round phi over round n. Instead of gradient psi dot n. So substitution these two expressions for diverge A and A dot n into the diverge theorem here. We obtain Green's first identity, this equation. We can write this equation. So we can use phi Laplacian psi here, gradient phi dot gradient psi, this one. Put these two part instead of diverge A in this equation, so you can have the left hand side by this form, and so you can use A dot n by this part. Put this part instead of A dot n here in the equation, right hand side, and dA is the same. So integral on surface is equal, this one is the same. A dot n changes with phi derivative of psi respect to the n. So you can equation 1.35 interchange phi and psi in 1.35. You just change these two and you can have another equation by this form, and just subtract this two above equation, I mean this equation and this equation, just subtract them. We obtain Green's second identity by this equation 1.35. Okay, let's try to next page. Green's theorem related volume integral to surface integral, and the volume integral contains the operator del 2. These features are useful for the manipulation of the Poisson equation in bounded space. For example, applying Green's second identity, you can have this one. Okay, we may convert the Poisson equation into an integral equation. Just in 1.35, the relation 35 here, just letting psi by 1 over x minus x prime, magnitude of x minus x prime, I mean. So del 2 1 over x minus x prime is equal minus 4 pi delta function. I let you know what is the delta function in the next lesson, inshallah, God willing. Okay, phi be the electrostatic potential in this equation. So Laplacian of phi is equal minus rho over epsilon 0, as you know. I before told you in the last sessions. And x prime be the integration variable. So the integration variable of this equation is x prime, not x. You should be careful by this. We obtained this equation, so just put this definitions in the relation 35, and you can reach to this equation here. So phi is equal 1 over 4 pi epsilon 0, and this equation here 1.36. 1.36 is an integral equation, not a solution. In fact, for phi in infinite space, we have phi proportional to 1 over r. R is the distance between the charge element and the observer, you know. Hence 1.36 relation reduces to phi is equal to this equation, and when you have phi proportional to 1 over r, you can have this relationship by this equation. Okay, let's try to next. I want to know you the solution of this equation, and by some boundary conditions. We have 3 boundary conditions in electromagnetism or electrodynamics: Dirichlet boundary condition, Neumann boundary condition, and Cauchy boundary condition, or Cauchy boundary condition. So what is the Dirichlet boundary condition? Boundary condition of Dirichlet is just specified by phi, but Neumann boundary conditions is specified by derivative of phi, and Cauchy boundary condition is related to both phi s and derivative of phi s. Both is specified, in fact. As another application of Green's theorem, we use it to prove the uniqueness theorem for the solution of the Poisson equation. Let there be two solutions, phi 1 and phi 2, which both satisfy by the equation. So the Poisson equation is with phi is equal phi n on the surface, I mean Dirichlet boundary condition, and round phi over round n is equal phi prime n on S for Neumann boundary condition. It means Laplacian of phi 1 is equal minus rho over epsilon 0, and Laplacian of phi 2 is equal minus rho over epsilon 0 with phi 1 2 with these two conditions. Define u as phi 1 minus phi 2, then Laplacian u is equal 0, as you know. I mean u is equal phi n minus phi n is equal 0, so, and or round u over round n is equal phi n prime minus phi n prime is equal 0 on surface. Rewrite Green's first identify, as you know, as I told you before. Let's try to this equation first. Green identify, this equation. So boundary condition u is equal 0, or derivative u over n is equal 0 on the surface, Neumann condition or Dirichlet condition. Dirichlet condition, phi is equal 0 on the surface. For Neumann conditions, derivative of phi over n is equal 0. You remember? So you put these conditions on the equation here, and you can have del u is equal 0 everywhere with within the volume, this volume, and u is equal phi minus phi 1. This u is equal 0 if u is equal 0 on the surface, or is equal constant because the derivative of u is equal 0. So u must be 0 or constant for the surface, on the surface. Phi 1 and phi 2 differ by at most a constant, hence are the same solution. This is the theorem or on the electromagnetic for boundary conditions. And since the solution is uniquely determined by specifying either phi or round phi over round n on the boundary condition, the Cauchy boundary conditions is an over a specification which may lead to inconsistency. As an exercise, you can prove that there cannot be any static E inside a closed hollow conductor if there is no charge in the hollow region. This is an exercise, and you can find the answer of this exercise. Okay, let me try to continue in the next file, and I leave you with the new file here, and goodbye, inshallah, till next lesson. Bye.